Oh, so you're chairing the session.
Yes. All right. Yes. Ladies and gentlemen, you know what time it is. It's time for Flash Talks. Yes. So everyone has 5 minutes time to present, and you can use it as you like. You can have 4 minutes present and then 1 minute for questions, for instance. And the first one is Laurent Gatto, please.
So I'll be talking about a very recent agreement, a collaboration between Bioconductor and Physalia. Laura already briefly mentioned it, but I would like to expand on it because I think it's an interesting, important opportunity. So for once, the weather was really gorgeous. It was hot, but not too hot. And it was end of March this year in Kenya, in Nairobi, in Kenya, for this bioconductor workshop that was already mentioned a couple of times. And Maria and I were having a beer, as you do occasionally, after a long day of work teaching there, and we were pretty pleased with ourselves. The learners were really motivated. The organization was flawless, fantastic place where we were. And we were quite honored, to be there and contribute and kind of teach these people that were really eager to learn. But of course, I would be delighted to go every month, in Africa, meet different people and teach there, but that doesn't scale. So we were trying to brainstorm, how can we facilitate these collaborations with a huge country or huge continent and lots of people that are eager to learn. And so, as it happens, we needed a second drink to really put ourselves in the mood to brainstorm, and realized that several instructors that were there in Nairobi were actually teaching for another organization, Physalia, which is a small company in Germany that organizes courses, and Carlo, the person behind Physalia, gets in touch with people that have some visibility and expertise in the topic and invites them to organize or to teach courses. So Physalia, they do all the logistics, which is a lot of work, takes a lot of time, and we have our teaching material, we come there, we teach, and that's it. And so these are paid for courses. For the course I teach, I think it's close to 400 euros for 3 days of 6 hours. So it's online. It used to be in person, but since COVID, I think it's mostly online, which I think is reasonable, but it's impossible to pay for the Global South. If you have a lab that can pay 400 euros, that's fine, but it's not a trivial amount of money. So we thought that, well, maybe there is a possibility here to start and work with Physalia and to open a place for people that can't afford to pay these hundreds of euros. And in Bioconductor, we have a place, a channel to discuss these opportunities when it comes to training. So the training committee is there to help and brainstorm these possibilities in terms of training. And so these can be informal discussions during our monthly meetings, but also more formal discussions with the technical and collaboratory community advisory board. And so, 3 months later, we came up with a proper agreement that was signed by all parties, so the teaching committee and Carlo for Physalia. And what this agreement defines is that, so in Bioconductor, we have certified or recognized instructors, that have some experience in terms of teaching and their kind of technical scientific expertise. And they will kind of be recognized as official or contributors for official bioconductor courses as part of Physalia. Many of these are already taught, and maybe also develop new courses. So there's this joint promotion and visibility of Physalia and bioconductor, and this short talk is one of these, increased visibility to get the word out. Physalia also help us organize courses. That's what they already do, but they also sponsor this conference. And when you organize conferences on a yearly basis, it's really important to have sponsors to be able to carry on these organizations. And arguably the most important output of this agreement is kind of accessibility and inclusion. So every courses that are taught by recognized by conductor instructors, and here are a few, come with 2 spots that are kind of free to attend from learners from the Global South. So here are a couple of courses that are already planned for this year, and hopefully we'll have many more in the coming future. And of course, you can always participate and pay, but if you're from the Global South, these are free. So these are the courses so far. And I think beyond this, the take-home message is, you know, there are lots of opportunities that we can seize, and generally these come up while interacting among each other. So, you know, please feel free to interact among yourselves, interact with the teaching committee if you're interested in helping out. We are always open for newcomers to try to, you know, diversify and increase the reach of what is produced and what is shared as part of the project. Thank you very much.
All right, thank you, Laurent. Then next one is Mark Robinson. Yes, I guess it's this one, maybe. You can try.
Okay. Good morning, everyone. I'm Mark from Zurich, and I want to tell you a little bit about our Omni Benchmark project. And first, just want to acknowledge some of the key players here, especially Izushkun, who's the kind of the key technical architect, Ben and Daniel, that are our main developers, Charlotte, who's given us advice over the years, and Almut, Anthony, Rachel, who have been involved in earlier versions of this. And so this is not really pure bioconductor, I would say. It's bioconductor adjacent. And the idea is it's all about benchmarking. So it's we're often flooded with tools, and we need to evaluate them, and we want to do this in kind of a good way. And I thought I'd start out by just making you think about this in maybe a potentially different way. So this is actually something I stole from a talk that I saw 6 years ago, but it kind of resonated with me and stuck with me. It was about it's actually a quote from this book, checking of each by each through public criticism, which is a little bit what we do when we benchmark things. We kind of put public criticism to it. And the idea in this book is that no one should get the final say. So that's really a little bit like our situation where we often have new methods, we often have new data sets, new tasks, and so on. So ultimately, no one should get the final say. And also, no one should have personal authority. So it's not one person's view of the situation. It's more of a public consensus of the view of maybe whether methods are performing and so on. And so that's maybe not exactly how how we've kind of formulated Omni Benchmark, but it's useful to think about it in this way. And maybe people have seen this paper before. Another common tension here that you come across is that, well, whenever you publish a paper, you have to show that your method is better than existing methods, and you're allowed to kind of do whatever you can to do that, be judge, jury, and executioner, and the result is that your new method is the best. So that's always there. Something we did a couple of years ago was look into benchmarks and see, well, what's in them? What do people do in here? And so we looked at various things. I won't go into too many details, but basically to say that input data is kind of always available. Sometimes there's really nice synthetic data. It's not often available or not easily available. And then the results of running methods on data sets is often not available. And we started to think whether some of these components are actually quite useful for the community. In many cases, they are. Also on the software side, often people quote the software versions that they use, but there's really no kind of reproducible containers or reproducible recipes for software that can be found. So we thought, well, that's maybe also something that we want to collect together. We also looked at the code from many of these benchmarks, and so the code's available. but it's not very extensible. These are kind of our opinions on some scale and so on. But anyways, the theme for all of this, for our thinking in the Omni Benchmark project, is that we want transparency. Transparency builds trust. There's a lot of interesting, useful benchmarking artifacts, and so maybe we should actually collect those when we build benchmarks. This business about extensibility and just thinking about standardization allows different tools, different projects to interoperate. So what does Omni Benchmark do? So basically, we start with a benchmark specification file, so I'll tell you what that is in a second. Omni Benchmark actually writes the workflow for you. Right now, it's a snake-make workflow, but it doesn't have to be. I know there are some Nextflow people here, and I'd be happy to speak with you. Basically, and then it runs a workflow. So then it generates all these artifacts. So all of the interesting, useful components of a benchmark are kind of captured in this. These can be shared, inspected, analyzed, and so on. It also does various validations. It's nothing to do with bioconductor in R. It's language agnostic. It's Python also. Here's a little bit of a schematic, and we also have verbs for this. So kind of planning at the planning stage. You can do this solo. You can do this in a collaboration. You can run it. Various flexibilities for that, and then inspect it, including dashboards that people here have also contributed to. The heart of this is this definition file, which you can see here. Here's a recipe for an apptainer software environment. And then we have these different stages, maybe for data, methods, and so on. And it's kind of all encapsulated in this definition file, and the definition is what you would need to build. Just to look a little bit closer, this is what an actually running definition is. It's basically, again, a recipe for software environments. It's pointing to GitHub repos that have the code to actually run things. Okay, last thing, how can I benchmark? So what you would need to do is install the package, and instead of writing your own workflow, you write the definition. So the definition defines everything, and then Omni Benchmark takes that and allows you. So you still have to do the same things. You still have to specify software environments and the stages and everything. It runs it, and then, yeah, you can do this as a team. You can think about it in the future where you can actually take someone's benchmark, you can fork it and run it on your own resources or add to it and so on, such that this is something that lives. And one thing that's, of course, on our mind is working together with some of the projects that are out there to develop open standards for this. I think my 5 minutes are up. Happy to discuss.
Thank you, Mark. Next one, Ellis Patrick. Yes, welcome. This one.
This one.
Yes. Or is it? Yes, it should be.
So today I'd just like to give a quick update on our SpicyR package, which a very talented student, Nick Kenyette, developed for testing changes in the arrangement of cells in highly multiplexed imaging data. And so whether you're testing for changes between two groups or associating those changes with survival or some other continuous outcome. So one of the neat things that Nick did was he designed this method to make it possible to compare between groups where different subjects could potentially have a different number of images, and he planned to leverage this information in an appropriate way. And so the default way that SpicyR calculates localization scores is with the K function, which Martin explained yesterday. That effectively goes around, and so in this situation, for every red cell, you would calculate the number of blue cells within a certain radius and then average those in some way. And so why am I speaking? Well, I'm speaking because I've got a great student called Sadiq who has been trying to extend SpicyR, and he hopes to get some functionality out in the next release. And so his extensions are to, instead of just using mixed models and t-tests to test for change in localization, he's implemented an approach that leverages generalized estimating equations. This also allows him to propagate confidence scores, so potentially if you're not so sure if a cell is a certain cell type, you can propagate that information through and we've improved the integration with our spatial package and also some other IMC packages. And so what's the consequence of all of this? Well, we get a dramatic increase in power, which is fantastic, and we control our false positive rate much more appropriately. And not only do we have more power, but when we do detect changes, the ranking of our lists are more appropriate. And so that's where we are. Again, I'd like to credit Sadiq and Shreya for putting some effort here, and I'm happy to chat to you in the break about the package.
Well, we could have some questions if there are. Well, you can chat during the break. Cool. Then next one is Ali Youssef. Yes. So you can use this or this one. Cool.
I know it's weird because you see only my head from here, but I'm Ali Youssef. I'm doing my PhD in Åbo Academy in Finland, in Turku. And I'm here today to talk about NMF batch, which is a unified framework for batch correction and imputation, especially for proteomics data, but I mean, it can be used also in other data. So in proteomics, we need first to understand what kind of missing value we have before trying to solve the imputation problem or the missing value problem. And we have like 3 different missing value. Missing not at random, missing completely at random, and missing at random. And each one have each specific imputation method, like you have to use it to be able to correctly impute for your missing value. And then the types of the biases or the technical bias that could arise especially from the MS batch, MS proteomics is 2 types: continuous batch effect, which is like the MS signal drift over the time, and discrete batch effect, which is usually come from digestion batch or TMT, different TMT sets. So we decided to trying to solve this problem using 2 steps. The first one is using NMF, which is the negative matrix factorization. And negative matrix factorization first try to reduce the protein matrix into 2 smaller matrices, which like H and W. And we are using this H to correct for the batch effect. And we are using generalized adaptive model in order to model these batches or any type of technical bias you want. Either is it discrete or continuous, which is very important because most of the tools doesn't allow you to correct for the continuous batch effect, which is the MS signal batch effect, which is not linear. So in many tools you can for sure correct for a continuous batch, but linearly. So with the generalized adaptive model, you can correct for it as a smooth factor because it's like a batch effect over time. Then we are multiplying the corrected H with the W to get the corrected matrix again. So the imputation is coming like at the end. So we have 3 options in the imputation method. We have imputation with a reconstruction, which is happening automatic when you are just multiplying W by the corrected H, or because the NMF here implemented without taking into consideration the missing value, so the batch effect or the batch correction effect is not affected by the missing value. So you can just use any other imputation method you would like, or we are trying now to create like a hybrid imputation method that use maybe entropy or something to detect if the missing value is coming completely at random or not at random, and imbued this specific missing value with like the correct imputation method. And we did like very initial benchmark for the imputation part. We have this proteomics data set, we masked the values, we created different missing values with different percentage randomly, we repeated it, and then we applied different imputation method. We correct the mean error, and as we can see here, okay, the NMF batch, it is like the second one, which is a very, very low error rate compared to other imputation method. But the important part is the batch effect. So we have this, it was from the GM, the omics GMF, actually, manuscript. So this data set is a single cell proteomics TMT data, and this is before batch correction on the left side, and in the right side we used here combat. This is very initial, we need to benchmark against other tools, but this is combat, which is the most, I can say, the most used batch correction method in bulk proteomics at least. And as we can see, still there's some batch effect, but after applying NMF batch, we can see a nice clustering in the PC according to the cell type and not the TMT sets. Yeah, so the preprint will be available soon, maybe next week on PyArchive, and we are preparing the package for PyConductor submission, and we will do for sure more benchmarking for this tool. And my group is not a bioinformatics group, so I'm working alone on this, so I'm happy to collaborate with anyone interested in these problems. Thank you.
Thank you, Ali. So next one is Kevin Roux Albrecht. Yes, welcome.
Yes. Thank you. Right, so the time has finally come to embarrass myself in front of everyone. After all the good science we've seen, I will show you what I'm doing with my time. It's recorded, right, so my PI can see it too, gather the evidence and justify why I'm not value for money. But yeah, this story starts like it usually does for me with messages from Federico saying, wouldn't it be nice? And yeah, so I don't see Laurent that often, but if he was there, I would have just told it, hold my beer. And yeah, so this, I've done it. It took far more time than I usually plan for those things because, as you'll see, I try not to go too technical, but you'll probably appreciate the effort I put in it. And yeah, so basically just in hopefully 5 minutes, I'll tell you how I made this thing and how you can feed it. But yeah, in my defense, I was left unsupervised. I've got a very trusting supervisor, so this kind of thing tends to happen more often than you'd expect. Yeah, so how did we get there? So you've seen the hexagon outside and the note on the website. So yeah, how do we get there? So there is, I think I've skipped the link. No, it's over, no, that's, anyway. The code is on GitHub because obviously I do things reproducibly. So step one, script number one, download all the BioC stickers, easy peasy, everyone here can do it. They're all listed on a very nice README. You scrap all the URLs and you download them because, I mean, I don't want, it takes a couple minutes to do it. I don't want to wait 2 minutes every time I do a new version of the poster, and there have been versions. So, and that leads me to the revealing the reason why BioC stickers repo exists. You never knew it, but you were contributing to a bigger thing. So, second step, and I'm not naming any names, but it's very funny when you try to automate things to see all the exceptions to the rules. And yeah, there were some stickers that were taking a weird amount of time to get processed. And I was like, I mean, they're stickers. So there were PNG files. Some of them were a little bit bigger than the others. So, oh, sorry, no, I'm jumping ahead. That's the next one. Cropping the stickers is actually, when you see a hexagonal sticker, Some of them come in hexagons with the alpha well set. Others come as a square with a white background, black background. So I was not going to do 200 stickers by hand, so obviously I scripted that. So yeah, to avoid being processed, please crop your stickers to hexagon. It makes my life easier. It makes future version. And yeah, you can always update your stickers. Yeah, so this is the process. Let's not go into the detail of it. There is a bit of sort of convex hull and things. So the script is there. And yeah, it works. I think someone pointed a few exceptions in there, so I may have missed a few. 3 and 4, some stickers were bigger than others, so higher resolution, bigger file size, and so on. So I didn't do the trimmed mean of pixel count or other normalization. I just went for the quantile and said if you're above that, you get downsampled. So that's just because I need to calculate the average color of the stickers to sort them. So that is how that bit happened. Count how many stickers, make a pixel rank plot. I mean, I try to reuse terms that we're all familiar with so that the concepts don't need to be explained. And of course, I'm citing my source, EuroBioC. I never used it in my work, but I finally got a reason for using it. So very nice transferable skills from that perspective. Downsampling pixel and calculating the average color. I mean, the average color is like the mean of red, green, and blue. I'm happy to get help to improve and get feedback for that. And sorting the stickers, again, a bunch of packages I had never seen before, but you know, Google, ChatGPT saying, how do I sort things by color? So my star methods are written right there. So I'm pretty pleased with the final results, but again, if anyone wants to have a go and find me a better sorting or feel like their package sticker is on the outskirts they want to bring into the middle, you know, there is a little bit of bias going in there. And yeah, so then the BioC node is processing, again, EuroBioC, processing the image, and then laying out the stickers very nicely as a gradient from one place to the other. I do need, there's a bit of manual downsampling in there to fit the number of tiles to the number of stickers I've got in my hands. And same thing, that was actually the easier part. The big hexagon, I actually had to like Google again, if you have hexagons, what is the spacing between them to create the grid? And that's how I got with what I call the bioconductor Death Star, which is there. So there is a DOI, as you may have seen from the website. I think we're getting there, and this is my closing slide. So where you guys come in, so all hands on hex. And Scotty, so I hope that you won't leave me alone in this enterprise. So that is, if you have a better way of sorting color, averaging color, look at, suggestion, come by my poster, it's 4 meters by 2. So I think you've seen it. Yeah, and with that.
Thank you, Kevin. And the next one is Dario Richelli. Welcome.
Hi. So for today, I want to let you know, if you don't know, that we have these working groups in Bioconductor, where a bunch of people have a meeting every now and then discussing things. And so I joined this one last year or so. And so the BioC classes working group has the aim of just wrap up all the classes that we have in Bioconductor and organize them as the core classes, the contributor classes, and also to understand how to improve the ecosystem in Bioconductor by integrating maybe the S7 framework that is coming up right now in R. We discuss things on Zulip thanks to the BioC classes channel. And so we have these main tracks so far. So as I was saying, we are collecting all the core and user contributing classes, and we are trying to give an overview of them, and how this ecosystem can be well presented to developers and users in order to reinvent the wheel anytime. And so I suppose that now we have to include also the IC experiment class inside our work. And finally, this new S7 class paradigm, which is arising, and we are trying to understand how this can be, because it does support natively the S7 class paradigm that we are using in bioconductors. So we are trying to understand which is the best way to move or interact with the bioconductor energy system with this new S7 class paradigm. So last thing, very, very flash talk, you can join our group because we need people and also new ideas and new things to, new points of view for this kind of things. So you can join easily the channel on Zulip. You can attend the meetings. We meet approximately once a month, but every now and then we skip a meeting, or just suggest issues on the GitHub. And if you have any other questions, you can reach any of us. The group members are these ones. You can easily find them, their names on our page. And that's it. Thank you.
Cool. Thank you, Dario. And last speaker is Kraine O'Mahony. Welcome.
Hello, I'm Grainne O'Mahony from the Limerick Digital Cancer Research Centre at the University of Limerick in Ireland. And today I'm presenting a package that we're currently developing that analyses variant prevalence within the AEC or GINI dataset. So the American Association for Cancer Research has put together the GINI project, which is a huge international collaboration of clinical cancer genomics data. It's currently in its 18th version and contains over 250,000 sequence samples from 210,000 patients in 20 centres from 7 different countries. Within the GINI dataset, we have data on somatic mutations, copy number alterations, and structural variants. There's also a number of additional variables, both patient demographics, such as age at sequencing, death, and last contact, as well as sex, primary race, ethnicity, the centre at which the patient receives their treatment, their vital status, year of last contact, and year of death. Additionally, there's many sample details involved in the dataset, including the cancer type defined by OncoTree code, the sample type that was taken, so if there's a primary tumour, metastases, or a lymph node, the sequencing assay used, and as well as the number of samples that patient has had taken, the fraction of the genome that is altered, and the mutation count within the sample. So the aim of our package is to calculate the prevalence of a variant of interest within a defined target population and also perform subgroup analysis with a single user input. And we do this by building on the CBio portal or package. So at the moment, to answer quite a simple question of how prevalent is my variant of interest within my target population, there's quite a few steps that need to be undertaken. So first of all, you need to identify the correct data set, the correct molecular profile. You need to filter the patients to only those meeting your target population criteria. Then additionally, filter the samples to only those meeting your sample criteria. The samples that are analysed using an assay that doesn't detect the variant of interest need to be excluded. Then you need to download the genetic data in the genes of interest. You need to link the genetic and clinical data, and then you can perform your overall variant prevalence calculation. However, if you want to subgroup analysis, there's then the additional steps of defining the intervals, subsetting the population into those intervals, and comparing between groups. So what our package proposes instead is something that looks like this. So cancer type is defined by a string of OncoTree codes. The target population can be defined using each of the patient demographic variables, so age, sex, primary race, ethnicity, or the centre which the patient was treated. The variants are indicated by both the genes of interest, but also the mutations of interest within those genes. Then additional sample requirements can be listed. So for instance, are we only interested in primary tumours or all tumour types? Are we only interested in the first sample taken from each patient, or are we interested in all samples taken from each patient? Then the type of subgroup analysis requested can also be submitted, and in the case of numerical variables, the interval can be defined. So if we look at the example here, This assesses for the prevalence of ESR1 and PIK3CA somatic mutations, EuroBB2 amplifications, and NTRK1 structural variants in women aged 55 and over with breast cancer. And it only takes into account the first primary tumour sample from each patient, and it involves a subgroup analysis by age with an interval of 10 years. And what our package proposes is that all of these steps now happen in the background, and what the function returns is an overall prevalence of each variant of interest within the target population. It also includes confidence intervals and the number of patients that were involved in the calculation, how many have the variant, how many don't. And the second part of the results involves subgroup analysis for each of the variables requested, and these results are returned in both tabular and graphical format. So overall, the package simplifies the process of calculating variant prevalence within a target population. So I'd like to thank AAC Origini for the huge effort that goes into creating and maintaining a database such as this. And I'd also like to thank Prof. Culhan and everyone in the Culhan lab, including Michael Lynch and Maria Doyle, who are here today, for their guidance and help in creating this package.
Thank you very much. Yes, that was it. That was all the